Okay, it's time for a review. This is TwoTrees' version of the extremely popular 3018 CNC. They actually reached out to ask if I would review their newest upcoming CNC, which has like a 40 by 40 inch work area, but I said, that thing's never gonna fit in my workshop. Can I have the smaller one instead? So here we are. I've actually wanted to get into CNC ever since high school and have always been curious of these classic beginner CNC type machines. Enough so that I came up with a design for one of my own at some point, though I got sidetracked by 3D printing and never ended up following through with it. Now, because this is supposed to be an honest and no-nonsense review of a product, I'm gonna skip my usual theatrics here and start with full disclosure. This machine was sent to me free of charge for purposes of this review. However, I did pay $25 of VAT on it since it came directly from China. So between that and the machine not being very expensive to begin with, I feel no obligation or anything to provide a favorable review. And of course, I did make TwoTrees agree to what amounts to a shortened version of the teaching tech review policy, just so I can freely speak my mind about the product without fearing lawyers coming after me. God bless Michael for making it open source. Why a shortened version, you may ask? Well, Michael's full policy is pretty extensive and covers a lot of specifics that felt inapplicable in this case. Plus, and here comes the real surprise, I am not Michael, and without the experience he has, I cannot necessarily draw any useful conclusions from the same tests he runs. And ultimately, my goal is to make an unbiased review, not copy someone else's. And while I don't have any past CNC experience to speak of, this means it should be a relatively realistic test of how beginner-friendly TwoTrees managed to make their model. And I'm definitely qualified to give my 2 cents on the quality of components and mechanical construction of the machine. So I think you can expect that to be my main focus here. And with all that being said, it's finally time to get it unboxed. Inside, we get an assembly instruction booklet. How comprehensive it is, we'll see later. A power cord, the X carriage, which comes pre-assembled with the 775 spindle and the Z-axis stepper, the maker-based DLC32 controller board version 2.1, which actually runs an ESP32 and supports Wi-Fi. A Ziploc bag with all the mounting hardware, a bunch of tools, a 10-pack of engraver bits, and a little cooling fan. The X and Y axis stepper motors, which looked so dinky compared to the big package that I felt the need to check whether they are actually NEMA 17. Turns out they are, but they're a weird intermediary size of 34mm instead of the usual 40. Then a couple of wires, the USB-A to B cable, and the size of the gantry, which are made from what I can only assume is 10mm Bakelite sheet, based on the product page listing aluminum, Bakelite, and acrylic as materials, because there are some actual pieces of acrylic too, to form a type of makeshift enclosure for the electronics. And the power supply, which feels surprisingly light for the 120 watts it's supposed to put out. Suspiciously lightweight, in fact. I'll have to look into that in a bit. And I mean that literally. Then there are some plastic bearing blocks with LM10W linear bearings, more Bakelite frame pieces, and finally some aluminum extrusion with pre-drilled and tapped holes. The smooth rods are just thrown in there as well, along with the T8 lead screws, something I am not a fan of. Precision components should come packaged individually in a foam bag or something, or at the very least a plastic bag to reduce the risk of them getting scratched and dinged up during shipping. Finally, we have the work table, which consists of a single giant-ass piece of aluminum extrusion. As the name of the machine implies, it is 30 centimeters long by 18 wide, and it weighs a lot accordingly. Now, I absolutely hate that things are seeming to take a left turn already, but I'm immediately not impressed with some of the things I'm seeing here. The surface treatment of the linear rods just is not up to snuff. For starters, they're quite obviously not chrome plated. For comparison, here's an actually good quality smooth rod I happen to own, and you can see it's not only a totally different color, but also has a mirror finish as opposed to whatever this is. Granted, I am nitpicking here. In the grand scheme of things, a slightly rough set of linear rods is not going to make a machine stop working on the spot, and I do consider unplated stainless steel rods an acceptable compromise in low-cost, low-stakes applications, which this definitely qualifies for. Nonetheless, I would have liked to see a decent surface polish at least. Plus, you can clearly see a couple of nicks and dents and scratches in these here, which just plain should not be the case with linear rods. Checking for straightness by rolling them across this marble top nightstand, which is about the flattest surface I have here in the shop, I can't immediately see any disastrous bend. Like, I can still hear the sound changing slightly when I roll them, but the same thing happens with the high quality smooth rod I showed earlier, just to a lesser extent really. Trying to give you any real numbers here would be futile, seeing as the marble surface is easily less flat than the rods are straight, so you'll just have to trust me that they're straight enough for a mini desktop CNC like this. For reference, here's what a hilariously bent rod looks like, where you can clearly see a gap between the table and the rod opening and closing periodically as I roll it back and forth. And while we're at it, checking the lead screws, I get about the same result. Maybe slightly worse than the rods, but still within reason considering the intended application here. Now, since the linear rails are hands down some of the most important parts of any CNC, let's check the bearings next. Because just sticking the bearing blocks on the rods, we're immediately greeted by what feels like an awful amount of play, but actually means nothing at all, because the inside of these linear bearings is slightly tighter in the middle than toward the ends, probably on purpose to prevent over-constrainment and alignment issues in assemblies, so it feels horribly loose when you test a single bearing for angular backlash like this, but when everything's properly constrained, the actual radial play is a lot less. And to get any indication of how much we're actually dealing with, I have to put together this little setup with the dial indicator. So the way this works should be pretty self-explanatory really, but if I just gently wiggle the rod up and down, it looks like I'm consistently getting between 20 and 30 microns of play between the rod and the linear bearing, which matches up perfectly with past experiences I've had with cheap linear rods and bearings. In general, bearings seem to be 20 to 30 microns oversized, so if you have a rod that is spot on or even undersized, excuse me for venturing onto dangerous territories with my wording here, you inevitably get backlash, which is why I personally do not like these rods with closed bearings, because I've never seen any that didn't. And after getting a whole tub of bearings as well as a dud set of rods that were completely bent in an attempt to find decent rails for my new 3D printer, I feel like I can talk on this issue a little bit. But back to matters at hand, these rods here are undersized by only about 10 to 15 microns as far as I can measure, so really the thickness of a decent chrome plating is all that's missing for a good fit. Overall, I declare the tolerances with these rails adequate. It's definitely a you get what you pay for kind of situation, as you will never find a rods plus LMX UU setup on any more professional CNC machine for good reason. What I will criticize, however, is that the bearings do feel quite crunchy compared to some of the other ones I have, which suggests low accuracy of the balls inside and will probably show up as surface artifacts on the parts you make with this machine to some extent. Interestingly, the Z-axis uses 8mm rods with extra long bearings, which fortunately do not appear to have any slack whatsoever. And considering what a mechanical disadvantage these bearings are at over the crazy leverage the cantilever spindle has, it better be that way, because with even just 10 microns of backlash here, you could chuck the whole thing in the trash straight away. But honestly, the rigidity just here seems surprisingly good for what it is. I definitely expected worse. Next up, the idler bearings supporting the other side of the lead screw feel a bit crunchy, probably due to the fact that this seal seems to have been crushed during insertion of the bearing with obviously inadequate tooling. The entire bearing is slightly askew with respect to the part. Nothing I can fix with a hammer, plus they are only freewheeling anyway, but worth mentioning. Checking the extrusions, they all seem to be satisfactory in terms of straightness. And that apparently means straighter than the rods themselves. Oopsie daisy. I guess that means I can try giving you some numbers for the straightness of the rods if I now have something to compare them against. Here's the most bent rod, and if I push it down on this end, you can see it rise on the other. So, if my feeler gauge is to be believed, we're getting about 0.2 millimeters of bend over the entire length. Like I said, not great, but considering the application here, it's good enough. Like, realistically, you're not going to notice this in the results. The rest of the machine will be a bottleneck way beforehand. The 15180 bait extrusion, though, is not as flat as I expected. It has a bit of a curve to it, and in one place I was able to get the 0.15mm shim underneath the ruler. I do not know how flat this stuff is in general though, so I'll refrain from judgment here, especially as this shouldn't be a huge issue in most use cases, compared to some other stuff. For example, the spindle runout. That's right, I'm getting almost 0.2 millimeters of runout right at the collet. Absolutely egregious. I don't even know what to say here. I know collets come in all shapes and sizes, and quality grades, and you easily get a dud if you go for the cheapest one, but the problem here is in fact the entire chuck, because if I put the dial indicator on the tapered inside, I still get around 0.15 millimeters of runout, which is a lot compared to the 0.1 my cheap Dremel tool has for the entire chuck, collet included. Sorry to rain on your parade, TwoTrees, but this is simply unacceptable. It practically renders the spindle unusable right out the gate, as your included pointy engraver bits will carve circles instead of dots on every plunge cut. Lucky for me, I actually have a complete replacement collet chuck, including spare collets attained from my abandoned DIY CNC project, so I can just swap this in and continue my testing here. However, to be a good reviewer, I'll have to anonymously reach out to TwoTrees customer support and at least ask what they have to say about this much runout. So I'll let you know how that went down at the end of the video. Well, we're off to a good start. I already stripped the stupid hex drive. I passionately hate hex drive grub screws. No matter how hard you try not to, you end up stripping it every time. Well, that escalated quickly. The grub screws are out, but the thing's still not wanting to come off. Whatever I do, I need to be careful not to destroy the motor in the process. Fortunately, the chuck can serve double duty as its very own gear puller if you know what you're doing, so this was solved rather quickly. And now for the million-dollar question. Is the motor shaft even straight? Yeah, 14-ish microns is honestly more than I expected. Looks like I am getting much better results close to the bearing as well as on the butt end of the motor, so the shaft being bent is probably at least part of the issue. Let's hope the chuck I got is any better. It certainly didn't have quite the bottom of the barrel price tag and looks much nicer. And surprise, surprise, it's a lot better. I mean, it's still pretty awful in the grand scheme of things, especially once we add the collet and the extra stick out of the router bit, but this is pretty close to what I calculated would be the best achievable result with the present bend in that motor shaft. But at least it's about on par with the rotary tools now, so all in all, my repair here was still a huge success. It only took getting rid of the included collet chuck. Maybe getting rid of the included spindle motor as well, and replacing it with one that doesn't have a bent shaft would yield even better results. Okay, last thing I wanted to check before finally moving on to assembling the whole shebang is the suspicious power supply. All the safety certifications printed on it are fake, as I know thanks to patron Sienna who checked out of interest, so my hopes for what's inside aren't exactly high, even though I don't really expect TwoTrees to put flagrantly dangerous power supplies into their products. I bet you didn't see that coming, huh? Unfortunately, this here is making me eat my words from earlier. It's even worse than I expected. To start off, there is absolutely no line filtering, as you can tell from all the interference suppression components missing from the board, which comes as no surprise at all really, given the line filter is always the first thing to go when they start skimping on components. But turning it around, there's also zero separation between the high and low voltage sides. If an arc were to punch through that bit of solder resist, you'd be getting straight up mains on the output. Which you might be getting after a while anyway, because the transformer itself is not double insulated. The secondary side is missing the silicone sheath around the enamel to ensure it won't ever come into contact with the live primary. Of course, then you also have the power switching transistor and output diode sharing the same heatsink, which is not grounded, by the way, to flip off anyone concerned about safety. I mean, just look at the loose transformer core. Also, the output smoothing capacitor is absolutely ridiculous. It's about a third the size it should be. You can even see the outline for a much bigger one in silk screen on the board. Anyway, I'm not going to fully reverse engineer this now, even though it's a simple enough design. All in all, I guess it's not the worst of the worst. At least it's not just a giant capacitive dropper straight up feeding mains to the output, and it doesn't look like it's going to instantly burst into flames. But it's also really sketchy, and I absolutely cannot recommend ever using it. It's probably only legal in third world countries, which definitely explains all the fake safety certifications. This is ridiculous, I'm absolutely pissed. Products just should not ship with a dangerous power supply. Like, I'm not expecting an expensive Meanwell or whatever brand PSU, but something at least a bit better than this. Just freaking use at least the right size of components for the board you designed. It shouldn't be that hard. Plus, this machine is not grounded, so plugging your computer into the same controller as this power supply, you also risk blowing up your computer as a bonus. Anyway, I think that's pretty much all the mechanical stuff covered. The few things I haven't mentioned seem fine to me. The stepper motors, for example, are very nondescript clones without even a part number on them, but after my recent video where I did a bunch of research on that topic, I'm pretty confident there's nothing inherently wrong with them, and they'll perform about as well as you could expect a stepper motor this size to perform in that application. The controller board I'll talk more about later once I've actually gotten to know it a bit. For now, I think I'm ready to assemble everything. Okay, here's something I have to mention. You do need calipers or something to assemble this properly because the mounting holes for the linear rods are quite a bit larger than the screws, allowing for a lot of movement of the rods before the screws are tightened. Now, one might argue about this being the necessary adjustability or whatever, but in reality it means you need to manually adjust the rods to be parallel in the first place with nothing to go from. The manual just tells you to loosen and tighten the screws on the carriage till it moves freely, but if the rods are completely out of whack because you didn't adjust those first, this is not going to do you much good, is it? If they had just put shallow counterbores on the inside of these side panels as like locating features for the rods to go into a little bit to make sure they are exactly where they should be before tightening the screws, everything would have been a lot easier to assemble. Yes, you then don't get any adjustability, but you don't need any if these parts are remotely accurate. And I know for a fact they are because they're CNC machined, and from what I was able to measure, the spacing on these holes is pretty darn close. So this little extra step really shouldn't be an issue in manufacturing. In any case, the alignment of the rails would be worlds better than what the uninitiated is gonna end up with by screwing things together willy-nilly like shown in the instruction manual. I mean, smooth is something entirely different than what you're gonna get with these bearings, but at least it has tightened up enough that I don't get any perceivable backlash from the bearings. Now, for a pleasant surprise, the bearings on this X carriage are significantly better and much less crunchy than what I just dealt with on the Y-axis. Just listen. Unfortunately, the entire carriage also has frightening amounts of play in like a rotational sense, so I guess these bearings must have a looser fit on the rods. Oh well. You win some, you lose some. And in that particular case, we can indeed be happy to have some adjustability of the rods, because the only way to at least try and remedy this is by moving the rods further apart to put some preload on the bearings in the hopes of taking out the slack. Okay, this seems to have helped to a degree, at least toward the ends anyway. In the middle, not so much. You can still hear it. Obviously, because the rods are simply going to bend, so if the lead screw doesn't manage to firm this up some more, it'll be a real problem, I tell you. So I guess I have to elaborate on what I said before about making the rods non-adjustable, and say the locating feature would be great on the Y-axis where the bearings are adjustable, but the X-axis where the bearings are rigidly mounted in the injection molded carriage has to stay the way it is, especially because this is also the only way to adjust spindle tram. And that's as far as the manual goes for assembly. There's not much in terms of cable management, you just get a bunch of zip ties to go to town with. Now, my impressions here from seeing the machine fully assembled, overall it feels sturdier than I imagined, despite the sides and front and rear frame pieces being made from plastic. Which isn't to say a whole lot, because the real issue with CNC routers like this is micro deflections of the bit causing chatter. Although I should really be talking about macro deflection here, since deflection of the spindle is something you get in abundance on this machine. A whole 0.5 millimeters in X, in part thanks to the slack in the linear bearings, and plenty more, almost twice that even, in Y depending how hard I push due to the smooth rods flexing. This is unfortunately to be expected on a simple rail system like that with floating rods and inherent to the design. Realistically, all you can reasonably expect this type of machine with its concomitant general lack of rigidity to do is engraving, since that doesn't involve removing large amounts of material. However, I know as well as you do that people are inevitably going to try cutting stuff on it regardless, so that is what I'm going to test it at too. And the first step will be getting it all set up on the computer. Now, it's worth noting that unlike most 3D printers these days, this machine did not come with an SD card containing test parts and stuff included. Instead, we merely get a QR code to a Dropbox type website chock full of ads that we can download the files from. This did include the executable for the control software of their choice, Candle, but with a good portion of the files named in Chinese, I felt slightly confused by that repository at best, so I ended up just Googling and downloading Candle directly from the official GitHub instead. Very much like with Universal G-Code Sender, installing it is not necessary, it just opens straight from the executable. Now, I was slightly taken aback by the fact that the controller didn't immediately power on upon being plugged in. It actually runs off the drive power from the machine's power supply instead of USB. But once I had that set up, it was easy to connect to it through Candle, and I had it moving in no time. And at that point, why not do a dry run of one of the example G-code files I managed to locate in their folder? Sure, let's engrave this set of Chinese characters, whatever they mean. And this was actually all there was to it. I just clicked run and it started. Pretty straightforward. Then again, in the grand scheme of things, running the example files is always the easy part. The real pitfalls are always hidden in making your own G-code files to run, cause that's when you suddenly need to consider feeds and speeds and the number of passes and that sort of stuff. Now, one thing I'm immediately noticing here is that out of the box, accelerations are set extremely conservative. Like, it takes ages to get up to speed. And looking at the console here, it turns out they're indeed set to 10 millimeters per second squared, like they say on their website, so at least it's correctly advertised, but in real life this does feel painfully slow, and I'll have to tinker with it to see if those are actually necessary, or if I can maybe get a bit more performance out of it. The firmware itself on this machine is some flavor of Gerbil ESP32, possibly Fluid NC, though I can't exactly tell you which one because it doesn't say so anywhere. Now, whether Gerbil is a reasonable choice for a CNC machine in 2025 with how many other more powerful options are out there these days is debatable, but as far as I know, every single one of these 3018 machines from any imaginable manufacturer, they all run on Gerbil, so it's like, what do you expect? At least it's the newest 1.1H version that was ported to 32-bit microcontrollers and I think padded with extra functionalities or something. Full disclosure, while I said at the beginning of the video that I'm new to CNC, I am somewhat familiar with Gerbil and Universal G-Code Sender from my pen plotter series. I just haven't ever used a 3-axis machine before to make parts, and I'm not fully in the know about what's currently going on out there with the software. And now, if you'll excuse me, before we move into the second round of testing, I really want to try getting something engraved first. The set of bolts they included for our work holding efforts is really more of an insult though, to be honest. I'd rather they hadn't bothered at all because these are totally the wrong size. For reference, an M8 carriage bolt is what actually fits these slots. Sure, let's engrave iPhone. Why? I don't know, it's one of the included sample files. Let's hit send and hope for the best. Ouch. It's already not going too well. that's it done. Yeah, I mean, probably went a little too deep there. That's partially my fault, I suppose. Yeah, not ideal. Let's try that again. Oh wow, that is state-of-the-art machining right there. I mean, what am I supposed to say here? Yes, these are my very first few attempts, and things might get better over time with some experience working around limitations here, but the amount of chatter I'm getting right out of the gate, even on this very light MDF cut, as a result of the single flute engraver bit and all of the aforementioned backlash issues in the rails, is astonishing. Also, the spindle does nowhere near the amount of RPM needed to properly cut wood with a small bit, and this is already at full speed. Which actually serves as a great segue to my next few tests: spindle RPM and power. Drum roll please, the maximum I'm getting at full blast is about 8,300 RPM. For reference, an ordinary Dremel does on the order of 5,000 to 35,000 RPM. Like I said, it's a bit on the slow side for wood. You tend to get better results at higher speeds, especially with small diameter router bits. Below 8,000 is probably a good range for plastic, but wood, not so much. And this is at full voltage. The power supply has this selector switch on it that lets you run the entire machine, including the spindle, at anywhere between 12 and 24 volts in sort of arbitrary increments, which is utterly pointless because there is no reason at all to ever run this machine at anything less than 24 volts, since you're just unnecessarily sacrificing maximum speed on the part of your stepper motors as well as the spindle. And if you ever need less than full spindle speed to cut something, you're obviously going to control it the normal way via PWM from the software, in which case having an adjustable power supply voltage would be inconvenient at best since it just messes with your percentages. And by running it at 12 volts, you're obviously cutting your maximum spindle speed in half as well. Anyway, measuring the power consumption of the spindle, I'm getting 350-ish milliamps at no load, and if I'm applying my very scientific handbrakes, pun intended, it easily shoots up to almost 3.5 amperes before I burn my fingers. At 24 volts, that means we're getting just short of 80 watts, so it's probably safe to say that this is supposed to be a 60-watt spindle. For good measure, I also decided to measure PSU voltage sag under load, and it looks pretty crummy, albeit not enough to matter in this case. Next up, mechanical repeatability on X seems totally fine. Looks like I can go back and forth all day long, and it'll still hit the same spot within 20 microns. I honestly don't see how this could possibly be off. It is a CNC after all, but better safe than sorry, so I'm checking anyway. In any case, just pushing down on the table next to the machine will deflect the needle much more, so this should be the least of your worries. Going very slow, I also can't see a lot of microstepping artifacting going on in the movement. I mean, you can just about make out a faint intermittency in the movement of the needle, but it's really totally fine. Much more concerning is the fact that I'm getting occasional little holdups in one direction on the y-axis. I think this is caused by the crunchy ball bearings occasionally getting stuck and the anti-backlash nut compressing until it breaks loose again, but this really only seems to happen at very low speeds and, like I said, only in one direction, so let's not sweat it. That being said, it's time to start messing with those speed dials. What I'm doing here is basically just increasing the accelerations, testing if it still works, cranking them up some more, checking again, but also testing if it feels like it still has enough torque to do some actual work, and so on. Exact same thing for the maximum speeds, except I unfortunately wasn't able to increase those nearly as much as the accelerations. There is just a limit to how fast you can make stepper motors go without losing all your torque. Okay, that was fun. I have no idea why on earth they set their accelerations to a measly 10 millimeters per second squared, because I was just able to make it go all the way up to 1000 no problem, and that still didn't seem like the limit. Ultimately, I settled on a comfortable 400 for the time being, since there didn't seem to be a huge advantage to going quite that fast. As far as maximum speeds are concerned, those 1500 millimeters per minute are indeed pretty much all you can expect if the power supply is set to 12 volts. If I try to go any faster, this is what happens. Yeah, it sounds terrible and gets stuck skipping steps every time. However, as soon as I crank the power supply up to 24 volts, things start to get real interesting, because now I can go all the way up to 2000 millimeters per minute, and here's what that looks like. Yeah, that's much more like it, especially with those much snappier accelerations. I was able to make it go even faster, all the way up to 3000 millimeters per minute, but at that point we're starting to make it sound terrible again, and with the torque drop off from the stepper motors, I felt like I potentially wasn't getting enough torque anymore for actual cutting operations, so 2000 seemed like a reasonable compromise for reliability's sake. By the way, the manual was pretty okay overall. I mean, we're not idiots. Though I guess I did have the unfair advantage of not exactly being a total novice when it comes to the basics of operating a CNC with a G-code sender and whatnot. Either case though, this is the point where I have to run a whole bunch of test cuts and engravings, which is something I am a complete noob at. So I'll get myself acquainted with CAM software and stuff off camera to present you with days worth of testing after just a silly time card meme.
1 week later.
And here we go. I think I now have a much better idea of what we can expect this thing to handle. Obviously, I can't pick up years of CNC experience in a couple of days, so my tests were more limited than I'd like, but I should still be able to give you a general idea here. First off, you'll notice I made some Y-axis way covers from folded paper, which is really obligatory unless you want all sorts of crap to get into the linear bearings, especially since, believe it or not, I have never seen linear bearings of this type where the wiper seal actually properly did its job. I really should have done the same thing on the X-axis and the Z-axis as well, as you can see here. Secondly, my first real project on this machine was this spoil board, which I faced to have an actually flat and level surface. But anyway, I may talk more about that later. The first thing I tested was engraving all sorts of materials ranging from softwood to hardwood, HDF, plastics, and even copper. Sort of. And unexpectedly, engraving is something this machine's actually pretty good at. Considering its price point anyway. Turns out, as long as you go extremely slow and remove only the tiniest amount of material at a time, you can do quite a lot. For wood, the structural integrity of the material itself is definitely the limiting factor in the detail you can achieve. Here I'm cutting stained poplar plywood at 120 millimeters per minute with full spindle speed and about 0.2 millimeters depth of cut. There is no chatter and the result is pretty much perfect. Crisp edges with virtually no burrs. Ignore this messed up spot here. The workpiece came off the machine, which was totally my fault for not sticking it down well enough. I redid it on the other side and it came out just as good. Of course, this is not the most challenging engraving, so I stepped it up a notch with these other ones, and the web here between the letters on the Gerbil logo is 1/4 millimeter or 10 mils in width, cross grain, and still mostly intact. Similar for this lotus flower, though more of the webs were knocked down, either by the machine or me brushing off the dust, I can't tell. Obviously this is far too small to be practical in this type of wood. Even more so these roses, I can't tell which of these fibers are part of the design and what's leftover dust. But there's definitely some very fine detail in the leaves completely missing. But that's only softwood. How does it fare in hardwood? Not much differently in fact. Here I'm doing beech plywood at the same feeds and speeds, and aside from raising a bit more of a burr, there's still no chatter. There's merely more of the fibrous shavings stuck to the valleys of the engraving that need to be cleaned off. With the roses, you can see some of the detail in the leaves survived, and the tiny webs in the Gerbil logo and the other flower are mostly intact this time. Next, I tried plastic. This ABS from a filament spool was no problem either. There is more swarf stuck in the engravings, but I think it's mostly a settings issue with the weird order in which my Inkscape extension for generating the G-code arranged the cuts. The fine webs on the Gerbil logo and the lotus flower are perfectly intact now, and even on the roses we can finally see the veins of the leaves. So I tried acrylic, and honestly, I think that's what this machine is best suited for. My settings certainly weren't ideal on this first attempt, but the result on all 4 of these graphics is definitely respectable. Put some LED edge lighting on it and Bob's your uncle. You've got yourself some nice decorations. In fact, I'll let you admire this for a little while longer to build tension for the grand culmination of my engraving efforts here. So, if it engraves wood and plastic so well, what else should I try? That's right, milling PCBs, because that's totally going to work on a machine riddled with backlash and rigidity issues, isn't it? Well, surprisingly, it does work. Only sort of course, but sort of nonetheless. I was getting some chatter unfortunately this time, which, while not really surprising considering the step up in hardness compared to plastic, caused the tip of the engraver bit to snap off after a while. So much for one of the many unwelcome ramifications of chatter. I replaced the bit and ran the whole G-code again so it could carry on where it stopped, albeit a bit slower, and this time I barely got any chatter. Drilling also went fairly uneventfully, and I was left with a board that, although you couldn't call it a resounding success by any stretch of the imagination, was at least electrically sound. Now, I decided to call it a failure regardless and tried again since there were several glaring issues. PCB milling just requires fairly high accuracy on the part of the machine since we're trying to consistently hit low tolerances, what with clearance between traces only being a couple of mils across. Looking at a high resolution scan here so we don't have to deal with lens distortion from my macro camera, you can immediately see that some traces are considerably thinner than others, even though my design used the same 20mm width for all of them. The edge on those also looks rather mangled, and guess what? They were cut in the first pass where I had all the chatter with the bit that broke off. Anything cut after that has an almost clean edge. And obviously it wasn't just the tracks that ended up too narrow, but many of the pads are undersized as well. The worst instance being these 3 over here for transistor, where the middle pad is just unacceptable really. Like, you can solder a component to it, but it's going to tear off in a heartbeat, taking the tracks with it. I redesigned the board with 30mm traces instead, as well as beefed up pads and ran it again, and I was once more met with unhealthy levels of vibration despite going slow at only 100mm per minute. It did finish though without a hitch besides cutting into the mounting screw, which incidentally left nothing more than a scratch despite the bit being carbide. The only plausible explanation for this chatter I could come up with is the remaining runout in the spindle, because remember, I still have 50 microns of runout here, and in my understanding with this specific type of V-engraver bit, it could sometimes lead to a situation where the opposite side of the cutting edge would get smashed into the material first by the spindle runout, depending on which way the bit was installed in the collet. Either way, the board finished alright, and here's the scan. Although all pads and traces are big enough now, and the board can definitely be used, it does look all the worse for wear. The chatter especially did a number on diagonal edges for some reason. So, as a conclusion, while PCBs with 30mm traces are totally feasible, and even 20mm might be possible if you're lucky enough to not get any chatter, it's pretty much only good for crude boards using chunky, old-fashioned through-hole components. Anything SMD smaller than maybe 1206 practically requires 10mm traces, so good luck getting an SOIC footprint to work. In other words, this thing mills PCBs roughly how an Ender 3 prints ABS, to cite one of my awesome patrons from when we discussed this on the Discord. But of course, the story doesn't end here because I had a lot of cutting tests to do as well. And let me preface this by saying, avoiding chatter while trying to actually remove material with this machine was practically impossible. Even tender poplar plywood was painful to listen to half the time, and it mostly got worse from there. However, despite the racket it made, the part finished alright and didn't look too bad, all things considered. There is a lot of tear out, but as far as I know, this is rather common for wood cut on a CNC, so I'm blaming it on the use of a spiral flute end mill instead of a more traditional router bit more than anything. I specifically designed this part to have something to measure outer and inner dimensions on, and cut it out of poplar plywood, beech plywood, HDF, ABS plastic, and finally solid spruce. Why is that one last instead of listed according to its hardness between poplar and beech plywood, you ask? Well, it's by far the most challenging one, trust me. I'll get to that in a bit. As expected, beechwood was worse than poplar in terms of induced chatter, but again, the end result looked fairly reasonable, until you take a closer look, which is where you see the telltale signs. Not only is the cut edge pretty rough on these diagonal portions, but things are totally off on this straight cut here. It's conspicuously out of square, and there's a lip along the bottom. Holding it against the light, you can clearly see the gouges left by the flailing end mill, and to nobody's surprise at all, the machine had an episode of severe chatter right during the second to last pass on this very edge. So, yeah, not exactly ideal. HDF, which is much more dense than this beech plywood, didn't chatter quite as badly, but instead it did so the entire time, as opposed to the intermittent fits of violent vibration mixed with periods of almost normal cutting like I got with genuine wood. The end result in HDF, after removing the crazy amount of tear out, was a bit better though. Most of the edges feel relatively flat, except this left one again, which feels distinctly wavy when I run my fingernail along it. My first attempt in plastic was a total disaster. I got lots of chatter, and at the lower RPM, the spindle really didn't have the torque required to take the cuts. Only after reducing the depth of cut to 0.1 millimeters did I hit a feed to speed ratio that didn't overload the spindle while still removing actual chips instead of melting through the plastic, and only caused minor chatter. This stuff leaves a nasty mess all over the machine though, due to the swerve being highly electrostatic. On the other hand, the result was far and away the nicest I'd gotten so far, with this one edge almost perfect, even though the other one still shows signs of chatter. Lastly, I tried solid spruce, just for kicks really, because I knew chatter would be epic with it, as anyone who's ever operated a router on lumber can confirm. The strong difference in density between the growth rings and the soft foamy stuff in between is just the bane of all cutting operations relying on the rigidity of your tool. And I was not disappointed. I almost feel bad subjecting your ears to it, but enjoy this brief montage of the most atrocious noise you've probably heard in a while. And the camera mic isn't even doing it justice. After this, you'd rightly assume the end result was beyond hope, but fear not, it could have been worse. The surface finish does look like from a miniature chainsaw, but aside from that, the general shape of the part is still correct. And perhaps most surprisingly, it's also still fairly accurate dimensionally. With the cross-grain edges, I got the most chatter on closer to spec even than the ones along the grain where chatter was less of an issue. And of course, the point of these parts was to measure accuracy, but checking all these with calipers, I unfortunately wasn't able to deduce anything particularly smart from the measurements. In general though, it's safe to say that the result will always be the best in homogeneous materials like plastic. Mine was only like 5/100ths oversized in X, and practically bang on in Y. Even the round feature is spot on, as is the hole. The HDF, having no wood grain to speak of, turned out almost as good, with both X and Y easily within 50 microns. Only the round feature ended up undersized by about twice that, and the inner hole is a bit on the large side as well. Poplar is also still fairly good at within plus minus 0.1 millimeters, which, assuming the number they mention in their marketing materials is indeed meant to delineate the plus minus tolerance and not overall deviation, is still perfectly in spec. The thinner 4mm one actually takes the cake for the straight cuts, which are off by only 0.02 millimeters in both axes. Where things slightly start to fall apart though is the beech plywood. Y is surprisingly still pretty much bang on, but the mangled left edge made the part grossly undersized in X, unfortunately. The round OD test feature is also out of spec, especially as it's noticeably not round considering how much the measurement varies when I rotate the part back and forth. The hole is oversized in X and undersized in Y, but still within spec as far as I can tell. Lastly, the solid spruce, which remains astonishingly accurate all things considered, although it does seem to depend on which one of the samples I measure, because this first one is just barely in spec with both dimensions, whereas the other one most certainly isn't. And the round feature turned out small on both, which seems to be a common theme here in general. So, all in all, I would say, while not suitable for anything sophisticated like PCB milling or whatever, the accuracy you can achieve with this CNC is still totally sufficient for small, general woodworking tasks. The parts I can casually pull off here are certainly a lot more accurate than anything I can easily achieve with a shop full of woodworking tools at my disposal. It's not that I can't cut a square within 0.1 millimeters of the target dimension on the table saw, but it's going to take some effort and a lot of trial and error setting up the saw. And this becomes especially true for more complex geometries like, for example, this nub, or basically anything where an accurate position of a hole is required. It's practically impossible to drill a hole within 0.1 millimeters of where it's supposed to end up using a drill press. Now, I'll leave it at that for the cutting test because this video is already over 2 months behind schedule and I'm starting to really get stressed about finishing it. As for some general observations, usability was pretty good. I had absolutely no issue of Gerbil being confusing and hard to pick up, which is something I've dealt with in the past. Of course, this may also be because I was already partially used to it from my pen plotter, but I think it mostly comes down to two things. The firmware is already fully set up and configured for this machine. Unless, of course, like me, you decide to immediately fix the acceleration setting. But more importantly, this machine has no limit switches, like in fact most of the other entry-level 3018s out there. I think for manufacturers it's mostly a cost-cutting thing, but a serendipitous side effect would be that it makes the machine a lot more beginner-friendly. Now, you might argue how important limit switches are for this and that feature you might need once in a blue moon, but realistically, for a machine like this, they really aren't. So far, I haven't missed them a single time playing around with this, and if you crash the machine, you crash it. That's it. It's not powerful enough to self-destruct. And as a beginner, the machine physically crashing because you started your job too close to the end of travel is far easier to wrap your head around than why your machine keeps screaming at you about soft limits being triggered. It just takes away a whole layer of complexity from the machine coordinate system counterintuitively being located in negative space for some reason, which always was a pain point of mine, or the positive work coordinates somehow being superimposed onto it. So throughout my testing here, I think I maybe got a single error message at most. Can't even remember anymore for sure because it was so trivial. Now, I said I'd waffle about the controller board some more too once I'd gotten to know it a bit, so here we go. It's actually my favorite part of the machine. The maker-based DLC32 certainly seems like a solid choice. Being based on an ESP32, it natively supports Wi-Fi, of course, and you get an SD card slot as well as EXP1 and EXP2 connectors for hooking up a screen, in addition to all the usual facilities for driving a CNC. It's actually way closer to a modern-ish 3D printer controller board than the traditional 8-bit Arduino and CNC Shield combo. However, there is a catch. The firmware this machine ships with is not configured for any such novelty functions, so you'll have to compile fresh firmware for it yourself. If you just stick in an SD card, nothing happens, unsurprisingly, and plugging in a screen, all I got was random flashing of the RGB LED. The only thing TwoTrees has made available in their Dropbox is a binary file of the configured firmware, which is no less in violation of Gerbils' GNU v3 license, unless I'm very mistaken. The compiled binary allows you to do a factory reinstall in case you totally messed things up, but basically nothing else. However, the beauty of a sort of open third-party controller like the MKS DLC32 is that the maker-based GitHub contains a PDF schematic as well as source files for the adapted Gerbil ESP32 firmware, which are distributed under the correct GPL3 license, meaning you can download, configure, and compile it to your heart's content, which paves the way for all sorts of upgrades. And speaking of upgrades, TwoTrees also offers the usual 500-watt air-cooled spindle upgrade, but if you want my totally honest opinion, there is absolutely no reason why you would want that. This 775 toy motor is absolutely fine for the job. And no, I'm not trying to be sarcastic here, I really mean it, because on this machine rigidity will always become a bottleneck way before this stinky motor ever will. A higher power spindle really does you no good at all. Maybe the higher RPM helps a little bit, but you can get the same here if you just overvolt this 775, which should be totally fine seeing as on the Alibaba page for this machine, the spindle is spec'd at 12 to 36 volts. Just be careful, the controller itself does not support 36 volts, so you'll need a separate MOSFET module if you want to keep controlling the spindle via G-code. The second upgrade TwoTrees offers is this round laser module you can install in place of the 775 spindle, and while this is definitely the best option for a low rigidity machine like this, and will certainly achieve pretty good results due to the lack of cutting forces, I honestly don't see the point in it, because in that case you might as well get a dedicated laser engraver which will work better, faster, and more reliably than this 2-in-1 solution which kind of sucks at either of them. Keep in mind, those last two are totally my opinion based on my experience with this machine. I haven't actually tested any of those upgrades, so I could be wrong, although I don't think I am. Now for the grand conclusion you've probably been waiting for, should you buy this machine? The simple answer, I think, is obvious. No. Considering how many flagrant quality control issues I found with this thing, there is no way I could possibly recommend it with a clear conscience. I do not expect a CNC in this price range to be anywhere near as polished or rigid as a Carvera, but there is a certain set of minimum requirements that this machine does not meet. As it stands, the only use case I could envision for it is these shallow engravings, since those weren't meaningfully impacted by the chatter and look quite nice, especially those in acrylic. However, if you need enough of these engravings to warrant purchasing a CNC machine, you're probably running some small business and would greatly benefit from a better machine that doesn't take the better part of an hour for something small like this. High school me would have probably had a blast with it for a few weeks, but ultimately the biggest takeaway from this is going to be that it would have been preferable to just save the money and spend it on a better, much more expensive machine down the road, because any attempt at upgrading one part of this one would soon escalate into replacing every single component. You just can't polish a turd. And I know I'm being harsh here, product design is hard, I'm doing some myself, but as a reviewer it's my duty to show how the product performs in some sort of real-world scenario. So, assuming the entire production run has the same issues as my sample here, the three things TwoTrees absolutely has to fix on this machine are: A. Spindle runout. A totally indicated runout of 0.2 millimeters right by the collet is absolutely unacceptable. It'll make any chatter I was already dealing with infinitely worse. I don't care how you do it, but the total runout measured at the end mill shank must be less than, or at most equal to, 0.05 millimeters. This is not an unreasonable ask given the $25 rotary tools, and my cheap drill press can do it just fine. B. Use X-axis bearings that fit the rods properly. The entire X-carriage wiggling around loosely on there is ultimately the straw that breaks the camel's back and leads to the majority of the chatter I was getting. I know it's hard to find bearings that fit properly, but here's an idea. There is a type of these linear bearings called adjustable, which has a slot down the length of it so it can be squeezed together. I don't know how these compare cost-wise, but it may be something worth looking into. At the end of the day, I just want the insane backlash of the X-carriage gone. The Y-axis is acceptable even if the bearings are nasty. Of course, I'd like to see less crunchy bearings there and the rods made from hardened chrome-plated steel instead of stainless, but I understand this may not be feasible without increasing the price of the machine. Can't have your cake and eat it too. And C, get a decent power supply. While this one admittedly held up surprisingly well so far, much to my chagrin, would have been hilarious if it had exploded on camera, this piece of junk is certainly less than confidence-inspiring. And I understand asking for something with North American and or European safety certifications would be delusional, but I still want something where at least basic electrical engineering best practices were followed, like for instance, decent separation between primary and secondary, and with half-decent components. Now, if, and only if those issues are adequately addressed by TwoTrees, there are 3 scenarios where buying this would totally make sense. If you build small RC airplanes and stuff, where you need small parts cut mostly from foam and balsa wood, there is no need to spend a lot of money. The rigidity of a 3018 like this would be just fine. Second, if you are a total beginner wanting to learn about and tinker with CNC, but aren't that invested in actually fabricating parts for some reason, this would be perfect because you don't risk ruining expensive hardware. And thirdly, if you just want to dip your toes into CNC because you don't know if it's something you even want to pursue, then the minimum possible investment just makes sense. If, on the other hand, you are serious about making stuff using CNC, I'm afraid you'll have to be prepared to spend quite a bit more to get a tool rather than a learning toy. In that case, you might have more luck with one of these fancier pimped up 3018s, like this Pro Ultra one from Lunny. I can only speculate on how well those would work, given I haven't tried one myself, but what I can tell, even just from the pictures, is that some much better design decisions were made, including using actual linear guide rails on X and much thicker rods on Y. They are also on a whole nother level in terms of pricing though. Now finally, you'll want to know how my exchange with the TwoTrees customer service regarding the outrageous spindle runout went. Here's the full conversation, just hit pause if you want to read it. But in a nutshell, I contacted the official email they listed among their contact information in the user manual from my personal email address to get the same experience any regular customer would instead of reviewer VIP treatment. And after 3 emails with ample video documentation of the issue, I got them to offer to walk me through the process of claiming a replacement collet chuck. This obviously was a dead end because I don't have an order number for a device I was sent for free, so I told them some cock and bull story about having found a replacement somewhere to shut down the conversation. And that's about all I have to say for today. I mean, I could go on for another hour, but I won't. You'll find a comprehensive list of specs for this machine, including any I may not have mentioned, in the video description. As usual, all relevant links are there too, including, ironically, a discount code for this CNC in case for some reason you want to buy it against better judgment. I want to say a big thanks to TwoTrees for sending this over for testing, and especially for being so incredibly patient waiting for this review. I'm really sorry it had to turn out as negative as it did. Had I known in advance this would be the case, I obviously wouldn't have asked to review it in the first place. But while not perfect, my TwoTrees 3D printer was rather sound mechanically, so I hope they'd also know what they're doing when it comes to CNC. Special thank you also to everyone supporting on Patreon. Those guys had a not insignificant influence on this video over on the Discord. It's amazing how much I still learn from just hearing different viewpoints and experiences from folks in the community. So yeah, hope you enjoyed. See you soon. Bye bye.